Hello, welcome to Monster Train. This is Off the Rails, lessons learned from Monster Train development. First of all, before getting started, I want to say thank you to the conference organizers and the whole roguelike community. Monster Train definitely benefited from this conference in a lot of ways. And I'm grateful to contribute and be a part of it. So thank you for having me. My name is Brian Cronin. I've been working in games now for about 16 years. I was an engineer on Monster Train, and I also did a lot of the design of clans, of cards, artifacts, characters, at least the initial design of that. It got iterated on quite a lot throughout development. And here are some of the other games I've worked on over the last 16 years. So what is Monster Train for anybody who hasn't played it, might not be familiar? It is a deck builder game. So you build a deck of cards, you take it through a series of challenges, and you upgrade it, improve it as you go. It does have a roguelike run structure. So, you take it into a battle, you upgrade it between the battle, you get gold, health, upgrades, all sorts of things throughout. It takes place in a weird version of hell, where you're taking this train called the Bone Shaker through these challenges to try and defeat the angels that are trying to take down hell, basically. And it has an expansive meta progression system. So you unlock cards and clans and artifacts, all sorts of things. There's a covenant rank system where it's a challenge system where you upgrade 25 different ranks. It has win streaks. It has all sorts of stuff that people really like in unlocking everything and completing their collection, basically. And it also has a pretty wild power curve. So this is the game called Dominion, the first deck builder game. And here's their copper card. For 1, you get 1 gold. And for 3 gold, you get 2 gold. So kind of demonstrating their power curve here is pretty moderate. This isn't a perfect one-to-one comparison, but here's one of our basic attack cards. Just for 1 ember, we call it, it's energy. For 1 ember, you deal 2 damage. Here's for 3 ember, you deal 100 damage, and it's piercing damage, and it damages everyone. So our game has a pretty wild power curve, and that's one of the characteristics I think people really like. Also, we have a lot of upgrades, so there's all sorts of different ways to upgrade. In this case, it's a character called Shadow Siege. You could upgrade characters, you could upgrade spells, and people really like to go wild with this and see just the crazy cards they could create through this system. And this game was built using Unity, but this talk is not focused on Unity. There will be some Unity screenshots. Don't let that scare you if you use Godot or Unreal. The principles I'm talking about can be applied to any sort of game engine. And it was released in May of 2020 by Shiny Shoes, the name of our company. And in August, we released it on the Switch. So these are the lessons that we'll go over. I won't talk about them all right now, but just to give you a little preview of what's going on here. So we'll start at the beginning. Lesson number 1, the prototype will become the product. I think we've all heard this before. This is just a prototype. We'll definitely throw it out before going into production. Don't worry. We all know this is a big lie. This is one of the first versions of Monster Train. For folks who've played the game, you're going to know some similarities. It had 3 different sort of layers you played on top of, 3 different floors, 3 different lanes you'd play on. You'd play down characters, monsters, you'd play spells. The big difference was this version was real time. So there was a bunch of timers running. The characters would attack each other at a fixed rate, and you'd gain energy at a fixed rate. The enemies, the hero waves would spawn at a fixed rate. So it was all time-based. It was real time. And this was you were trying to move fast. We were iterating quickly, prototyping, trying a bunch of stuff. So that's what we built it starting off as. And it eventually turned into what it is today, a turn-based, deck builder game. So no more timers. It's all just, play turn-based like a traditional card game. But a lot of the bones of this code, a lot of the core architecture of this code are the same. This game and this game are the same in a lot of ways when you dig down and look at the code inside, So we never really had the chance to rewrite everything. We just kind of were going forward at all times. So this led to a lot of problems, as these generic Google image searches for problems can demonstrate. First of all, we took advantage of coroutines, which are an excellent tool when used properly. For anyone who might not know, I'll briefly explain what a coroutine is. And sorry, this is the programmery section of this talk. There are some stuff, if you're a pure designer out there, there are things you'll get out of this, but I am a programmer, so. A coroutine basically takes something that happens over time, and it expresses it in a single file, single function. It's all just right there. So in this example, maybe a unit is taking damage. We're going to reduce its HP. We have a damage animation, maybe VFX. We're going to wait for those to finish. If the HP is less than 0, we're going to trigger some death effects. Maybe this unit explodes when it dies, and there's more death animations. So basically, this is all happening over a period of 2 seconds, but we're expressing it all in just one function here. So the big advantage of this is just the sequencing is clear. It's like building Legos. It's 1, 2, 3, 4, 5, 6. It's very obvious what's happening. It looks very natural. It's very natural to program with this. There are alternatives to this approach. You might have an event system. There's all sorts of different ways you can abstract it away. And these have all sorts of advantages in and of themselves, but the big disadvantage a system like this has is you start splitting everything up into different files. Logic is dispersed in many different places. So that logic becomes difficult to follow. If you're building Legos, you have to move between all sorts of different pages to build that robot. But the big disadvantage of coroutines is there's no separation of concern. So the UI, sound effects, data, game simulation, they're all bundled up together in one spot. That led to some bigger problems. Eventually, we implemented damage previews. So combat in our game is relatively simple. It's like a fixed set of rules determine when units attack and who they attack. But when you start layering in a lot of units into the room and a lot of different status effects, it becomes complicated to track what's going to happen. So as an example, here we have a unit on the left. It has a red X above its 20 health, showing that it's going to die when battle starts at the end of the turn. But if we play a torch on one of the enemies on the right, that changes the calculation entirely. So now it's going to take 15 damage, and one of the units on the right is going to die. So just playing one single card changes the outcome of the battle significantly. And we learned that the player needed this tool. They needed to have a preview of what's going to happen. We didn't want the game to be a math puzzle. It was more of higher level decisions. So what would be great is if we had a fully deterministic game simulation. And what that means, if you're not familiar, determinism just means if I were to knock over this domino here, 2 minutes later, this domino here is going to fall over. And that's going to happen every single time I push these dominoes over. So there's a lot of reasons why your simulation might not be deterministic, and a lot of these were a factor in Monster Train. Maybe your starting state in random number generator is not using a fixed seed. You might be using floating points on different platforms. Those can result in indeterminism. There's all sorts of reasons. Some of these were a problem for us. Some of them weren't. What ended up happening is because we had basically a giant coroutine running the whole game, we had a lot of exceptions within that. So there were cases where if I'm in preview mode, I don't want to play a sound effect. That won't sound right. Or I don't want to show an error message. There's all sorts of reasons for, all sorts of exceptions to, make preview mode work. Another problem was that of how do we represent a card? And, cards are complicated, and I couldn't really find a good way to represent a card. So that leads us into the second lesson, which is cards are basically a programming language. So cards are awesome. I love cards. If you're a card gamer, I think it's just something, you see a binder full of cards, and it's an exciting moment. Just looking at what do they all do, where can I find interaction points and synergies, and there are these little components that when you add them up, they create something greater than any individual card. I fell in love with cards with this game called Netrunner. There might be some of you in the audience that recognize some of these cards. It's a great game. That's sort of where I fell in love with cards. And so as we went into Monster Train, this was going to be my first digital card game. And I've been programming games for a long time, but I never had programmed a card game of this scale. So the question immediately came up of how do I represent these cards? How do I architect the game code to support this? What does the data look like? How do the designers manipulate these cards? I searched online, and there was surprisingly little information on how cards are represented in digital card games. And so, I'm sharing this information in hopes to spread the knowledge, and there's some things we got right and a lot of things I think we got wrong that could have been improved. Another point with this I want to point out is there's no standard way to represent a card. If you think about a first-person shooter or a platformer, there's a lot of things that have been learned over time and have, like, coyote time has a term that people can commonly understand what that means. So there's nothing like that with digital card games. It's the Wild West. It's not well defined in how you represent cards. So I figured it'd be good to break down how one of our cards works. It's the simplest card in the game, probably. It's called Torch. So for 1 Ember, this is our energy or mana system. It's just called Ember. You deal 2 damage to a target of your choice. So again, very basic card. This is what it looks like. And again, don't be intimidated by the Unity aspect here. This is just data that's being visualized. So we have a title, we have a description. This is all localized internally, and we can tie into the effect itself. So this is deal 2 damage. If we change the 2 to a 3, the text will automatically update. That was a cool aspect we did. And you could define the cost here, the card type, rarity, just some fields that kind of meta fields that are important. And this is the bulk of what it does, the card effects. There's a lot of parameters here, and actually a lot of them are not used for this card effect in particular. So I kind of trimmed it down just to make it easier to understand. So a lot of cards that have multiple effects, but this Torch card has just one effect, which is to do damage. There's all sorts of card effects that we created. These are all ultimately these are code. Card effect damage it's cardeffectdamage.cs. It's just code, and we have a bunch of card effects, and it's saying the target is where I'm dropping the card. We have all sorts of different target modes. You could target all friendly players in the room to heal them, target all enemy players, target all characters. There are all sorts of different ways to target. Should test, I'm not going to worry about too much right now, but param_int, just saying, in this case, do 2 damage, but param_int is a sort of a generic thing. A lot of different effects will use it in different ways. At the bottom, we have ways to link it up to a class, tell it when it's unlocked. Again, just more kind of meta fields here. So I'll kind of go over at a very high level how we resolve the card in code. And again, this is going to demonstrate a point at the end here. So in our hand UI code, we know when a card has been dropped on something. So we're going to go into the card manager and play that card. In the player manager, we're going to remove energy, or what we call Ember, from the player face inside. And if they don't have the energy, then we don't play the card. For each card effect, we're going to iterate over each card effect, and we're going to apply the effect. And each card effect is just kind of has we inherit off of this card effect, and each one does whatever it's going to do. So here's kind of what card effect damage looks like. And, don't worry about, I'm not going to go through this line by line, but, we calculate the damage amount. In this case, it's just going to give us 2 because 2 is the integer parameter. There's some sound effect code. And ultimately, we're going to tell the combat manager to apply damage to a target. Damage amount and target. Those are sort of provided to us. We have a list of targets we kind of iterate through. Some parameters are passed in. Again, not super important here. And so the great thing about this is it worked fine if we had sort of an unrelated list of linear effects. Do this and then draw 2 cards, and that sort of thing. This system worked great for, no problems. But it broke down when we had effects that were dependent on each other or dependent on other game state, and when they interacted in nonlinear ways. So an example of that would be this card Vent. It's similar to Torch. The major difference here is it has a play cost of X. So instead of you spending 1, you're going to spend all of your remaining Ember. So you might have 3 Ember remaining in your turn. You're going to spend all of that. And you're going to deal 2x damage. So you might deal 6 damage in this example to all the enemy units. So similar but different in some core ways. And the main way it's different is how this X works, how the damage is calculated. So that's where we get into traits. There's all sorts of different card traits that a card could have. One might be piercing. It might ignore armor. That's an example of a card trait. This is sort of a hidden trait. It's just affecting how damage is calculated. So this is, again, just code, card trait scaling add damage. It's saying scale 2 times the played cost of this card this turn. So that's what these parameters are saying. There's different ways to configure these parameters and to scale in all sorts of different ways. So here's what card trait scaling add damage looks like. Again, not going to go through too much line by line, but it has a way to calculate the extra damage. It's based off of those parameters that I showed here. And it's going to return that as extra damage here. So when we have this function in our character state class, confusingly enough, to calculate the bonus damage, so when we're going to apply damage to this character, we're looking at the card that was responsible for that damage, and we're going to iterate through its traits, and we're going to calculate any kind of bonus damage to apply. So that's all how it's hooked up. The major problem with this is that the behavior is very implicit in code. The engineers are responsible for too much of the behavior. And card games are really complicated. Once you build out enough cards, there's a lot of interactions, a lot of ways that it's all twisted up. I don't know how to describe it better, but they're very complicated. And so we ended up having to write a lot of new code for even simple changes. So we had dozens of these card traits that we eventually created, and some of them were created for very specific cards. We'd write code in a lot of cases for if we had to do a new card that was doing something a little bit different than what all the other cards had done, which was a lot of our cards. We had to write some new code for that card. So the solution to this in my mind, or an improvement I should say, maybe not solution, is to use graphs in some way. So this might be what a graph looks like. This is just an example. Don't worry about the details here. But I wanted to kind of demonstrate how this might look like on one of Monster Train's cards. So here's Awoken's Rail Spike. Similar again, it's X cost, and it's going to draw X and apply -1 cost to those cards that we draw. It's also going to consume, so that means it can only be played once per battle. So I wanted to focus on this card and show you what a graph might look like to represent this card. And this is sort of what the designer is going to use to define the behavior of this card. So here's a graph. The green represents the flow, so it's going to start in the entry, it's going to draw cards, upgrade them, and then consume cards. So the entry, we're going to draw cards, and how many cards should we draw? Well, that's hooked up to the amount of energy we spent. And action params is going to be something you could add to this graph, a node you can add to hook up all sorts of different parameters. So we're going to draw cards for every energy we spent. You might have sort of a 2x multiplier in here if you wanted to draw 2x the amount of energy spent. And then we're going to go and upgrade cards. And what cards are we going to upgrade? Well, we're going to upgrade the cards that we just drew. So that card list is right here. And what are we going to upgrade them with? The upgrade data comes from the parameters here. This is something the designer can pipe into this graph. So we can even reuse this graph for multiple cards perhaps. And then we want to consume cards. And what cards are we going to consume? Well, we're going to consume the card that was just played. So we're not consuming any of the cards we just drew, it's just the card that we played. So that might be how this card is represented as a graph. We might want to change it so that now we're going to draw one card for every card in the discard pile. So the change here is right here, number of cards to draw. We have a deck info node, and it's going to be based off the size of the discard pile. So that's the only change here, and we've very dramatically changed what this card does with one simple change, and no code needed to be written. It's all just represented in this graph. Lesson 3 is that feedback and iteration are super important. And we had a system in Monster Train that I just wanted to share. I think a lot of games could use a system like this. It's not trivial to create, but this was probably the single most useful tool we had in the game. And I think without this, I don't think the game would have been nearly as successful as it was. So basically at the bottom left here, you can see press F8 to give feedback. So this is it's not visible on the screen in the version of the game that is on Steam now, but F8 is still, if you go into the game and press F8, the feedback thing comes up and we still collect the feedback at this point. But we were displaying it during the beta, so people knew it was there. This is a video showing how it works. So you might see this card, it looks really cool, you like the artwork, you press F8, you write a message here, and you click the submit button. And that's all the player needs to do. So it's very much zero friction for them. They don't have to alt-tab to any website. They don't need to have any username and password entry, no accounts. It's right there in the game. Press F8, type a message, done. From the developer perspective, it shows up in one of our Slack. We have a Slack chat room where it gives us some basic information about who sent this in, what build they were on, maybe a run ID we can look up in our backend, the time, the comment. That's what we see. But when we go into the thread that it posts, there's all sorts of useful information. So we have the game log. If they have an exception in there, that could be extremely useful to know. It tells us, we log a lot of information as the game is playing. So what card they played, how much energy was spent, all sorts of stuff. We also have a save file. So the save file, super useful. We had some level of determinism in the game where we were able to at least go to the start of the battle that they were in. And then from there, if we can infer what had happened, we might be able to reproduce their problem. And we also have a screenshot giving us more context. So the screenshot is also super useful. Sometimes it's just something very obvious. You could just look at the screenshot and say, oh, I know what the problem is. So phase 1 is collect the valuable player feedback. Phase 3 is profit. Phase 2 is the most important aspect to this whole system, which is just to take consistent action. So it's awesome to be collecting all this stuff, maybe shoving it in some database or a Slack channel. But if no one's taken any action, it was a lot of wasted effort. So we had a great producer on Monster Train that would look at this feedback every day, and we'd get it filed to the right person, and we'd at least consider every bit of feedback. And a lot of feedback we took direct action on and helped us fix bugs, and it was really great. And players love it too, because in some cases our really dedicated players would submit feedback, and maybe by the next day they would have a fix to whatever problem they submitted, or an improvement to UI or whatever. So I really recommend you collect and take action on all feedback. And I really mean all feedback. Even if you're just considering it, if you're like, oh, that's an idea, but we don't like it at this point. At least that you're looking it over is the first step. So it's really, really, really powerful. The final lesson is that mixing gameplay logic with presentation is fun until it's not. And this is a culmination of a lot of what I've already spoken about today. So here's an example. This is actually not Monster Train code, but it's just an example of how you might represent a card. So you might have a list of effects, and then when it's clicked on, UI code might call this onClicked function. It's going to play. We have a sound effect we're going to play. We're going to iterate over the game effects here, and we're going to resolve them. And then we're going to start a discard animation. At the end of that, we're going to actually discard it, and then we're going to play a sound effect. So that seems reasonable. That might be a way that you represent a card. I wanted to drill down into this. So what happens when you discard? In our card manager, we have a list of cards in hand, cards in the discard. We're going to shift the cards around. Very simple. Later on, it turns out that we're creating a new type of card, and we need to tell the card to do something when it's discarded. So there's all sorts of ways a card can get discarded, so we need to have a callback here. So we tell the card, hey, you've been discarded. At this point, we have special list of discard effects that we're going to resolve. And again, this all looks reasonable. I think in hindsight, this is how we wrote a lot of the Monster Train code. And in hindsight, I think this is a really bad way to structure code. And it's the way that I've structured a lot of my game code in the past. So I'm being very self-critical here. But it's sort of an object-oriented approach, and I think it has a lot of negatives that only come up toward the end of a significant project. And the main disadvantage here is it's spaghetti-like, everything's calling back into each other. There's no flow. It's just anything could do anything it wants at any time. There's these kind of global singleton-like managers that we call into that call back into cards that call into. So it's all over the place. It's wild. It ends up looking like this. And I love this screenshot. Do not touch any of these wires. And that's the feeling you get at the end of a game if you've been working on the game like this long enough. It drives you crazy, So how do you make spaghetti? Well, I think it's the folly of mixing gameplay logic with animation, input, and UI. And it's important to point out that game engines often naturally lead us to this dynamic. It's not anything Unity is doing in particular. The same dynamic happens in Unreal and all sorts of game engines. It's just, in this example, we have all these components on the single game object, and they're, in many cases interacting with each other and have references to each other, and they're calling into each other and out and all over the place. So what I'm an advocate for is splitting up your kind of pure game simulation into its own thing that it's its own isolated little box. It's a black box. So in this example, we have world state just represents the state of the world as pure data. So it's going to have things like the positions of units, their health, status effects they have on them, whatever, And world engine is responsible for manipulating that world state. So the world engine doesn't have any state of its own. It's just going to take these commands. So example, world command move or play card or damage a unit. It's going to apply those commands and affect the world state. And out of that world engine will come this list of world state changes. So here's a unit moved, a card was played, maybe a unit died. That's the output of the world engine. So it's a very simple flow, input, output, and the state in between. Some of you might recognize this as the model view controller. There's other names for this, but where the model is the state, this might be a database in the web world. It's just in memory, or a file. And the controller is what's the logic, what's affecting that data, and the view of that are these world state changes. So there's a lot of advantages to this approach. I'll demonstrate some here. One is, and actually this is all abstract. There's nothing displayed on the screen at this point. It's just an abstract simulation. So we need to actually display something and have sound effects. So in response to move, we might have footsteps. So we have a sound system applying those sound effects. If for a card played, we have card play sounds. We have an achievement system, so we know that they've played their 50th spell this game. And if they die, well, there's sound effects, there's achievements, and there's animation, there's VFX, there's all sorts of systems that want to know about that. But at this point, this is all isolated from the simulation itself. This is just a list of, hey, here's what happened, and the game systems respond to that. Another great advantage is that you can very easily, well, I shouldn't say easily, but it's much easier to save the state of the world. So you can kind of serialize this world state out to a JSON file. If you want to reload, get that back in, you can put it back into the world state. And none of the other game systems need to be aware of that on some level, at least. It's also great for networking. Now you can synchronize this world state over the network, and your other game systems can be abstracted from that fact to some degree. So I'm a big advocate of this approach. It's what we've started moving to this approach on other games at the studio, and I do this on my own personal project, and I'm a big advocate for it. So that's all I got for now. Thanks for hanging out. My email is there at the bottom left, along with my Twitter handle. If you want to reach out about anything, if you have questions, comments, nitpicks about what I spoke about, please don't hesitate to reach out. Thank you for your time.